This is the final presentation for Group 16, Senior Design 2, Fall 2024. Our project is called COMET, which stands for Celestial Observation and Mapping Using Engineering Technology. Our group consists of 2 computer engineers and 2 electrical engineers. One of the computer engineers consists of myself, Nicola, and the other one consists of Amber. And the 2 electrical engineers are Alexei and Carson. First, we want to extend our gratitude and acknowledgement to the Florida Space Institute, as with their resources and with their help, they were able to help us make this project flourish and sponsor us and give us the necessary resources to make this happen. The motivation and background for this project is that the Florida Space Institute, also known as FSI for short, was inspired by the Arecibo radio telescope that was based in Puerto Rico, and they wanted to have miniature radio telescopes implanted at different K through 12 institutions to essentially allow children or students to essentially learn about radio astronomy and provide a more real life application, a more of a in-depth interactions with the topic of radio astronomy, and essentially give them a more of an interactive experience and learning. The main goals and objectives for COMET follow as such. We have 2 objectives, one of them being the radio map and the other one being the radio telescope itself. For the radio map, we essentially want the user to input the frequency of interest to obtain radio signals, and to be able to display those radio signals that was processed by our single board computer to a radio map that could be obtained for further analysis. And we also want this information to be able to be transferable to their local machine for better hardware and or their personal lab. And we also want this information to be displayed on the LCD touch display as well. For the radio telescope, we want this radio telescope to be 3D printable, as FSI with their other projects also have 3D printable capabilities. The 3D printable capability allows our radio telescope to be easily manufactured and placed in the different K through 12 institutions, essentially allowing for more outreach within the community. And for the radio telescope, we want to use stepper motors that essentially allow us to angle the parabolic dish in a fashion where we can essentially keep the celestial body of interest in the center of our radio telescope to essentially get a better and more concentrated signal. And we also want to have a single board computer with an SDR receiver to capture and process the radio signals.
This is our table of engineering specifications. We have 3 major specifications that we really need to meet. First being the dish gain of 9 dB. The Raspberry Pi, we want the total amount of time from when we start the data collection to when the heat map is plotted to be less than 5 minutes. And our stepper motors, the rotational speed to be X degrees per second.
This is our high-level block diagram. The power source is a 12.8 volt 6 amp battery whose power will go through all of the regulator boards. The 12 volt regulator will power the motors. A 3.3 volt regulator will power the ESP32 and be the logic supply voltage for the motor controllers. Then the 5 volt regulator will power the Raspberry Pi. The ESP32 sends signals to the DRV8825 motor controllers to point the antenna towards the correct coordinates, and this is communicated through the user input from an LCD touch display connected to the Raspberry Pi. The type of motors that we decided to use were stepper motors due to their accuracy while moving. The stepper motors that we used were the Stepper Online NEMA 17 bipolar motors. This is due to them being supplied by our sponsor.
Why we chose the DRV8825 stepper motor driver. The stepper motor driver is the best choice for our design. Its simplicity is one of the key aspects that made the decision of selecting this stepper motor driver final. The voltage requirements to supplement this driver is one of the lowest of the drivers in this comparison, and this allows us to build a power supply unit that does not require supplement of a lot of voltage, meaning we can opt for a lower voltage but a cheaper battery as well. Also, this would put a lot less stress on regulators since the stepping down of the voltage would not be significant for other components. This stepper motor driver is also supplemented by Florida Space Institute, our sponsor, and the stepper motor driver is something that they've recommended to us because of the ease of use and their familiarity with it. Also, the DRV8825 stepper motor driver is compatible with the NEMA 17 stepper motor and the ESP32, which are the two components that are being utilized to provide the manipulation of the radio dish to track the celestial objects in space. Also, since this is one of the cheapest, we can get numerous stepper motor drivers for testing to ensure that it can work, and if one were to break due to an unforeseen mishandling, it can easily be replaced. Also, the simplicity of the design made it very easy to replicate onto a custom PCB.
For microcontrollers, we decided to go with the ESP32. Originally, we were going to go with the Arduino Atmega 2560 because our sponsor can provide us with this microcontroller, but due to recent knowledge of the chip obtaining ESD damages, we decided not to go with it, as for our custom PCBs, putting this chip on our own PCBs will provide unnecessary hassle and give us a hard time. So we decided to go with the ESP32 after talking with our sponsor. And the ESP32 is just as good of a choice as the Atmega 2560. It provides enough GPIO pins to interface with the stepper motor drivers, and also the operating voltage is pretty low compared to the Arduino Atmega 2560, which is better for overall power consumption, and the cost is a lot more affordable. And the durability of the chip itself, meaning it can not really suffer from ESD damages as easily as the Arduino. And also the compatibility and the performance of the chip itself being dual core and all of those cool features, it essentially made us wanted to go with this chip, and we thought it would be a good option.
Single board computer selection, we have decided to go with the Raspberry Pi 4 instead of recently using the Potato, mainly because it provided more RAM and the Wi-Fi connection was easier, as well as the integration with the ESP32. We are processing a lot of information with obtaining those signals, and the Potato sadly just wasn't able to meet those requirements, even though our sponsors wanted us to go with that decision. But the Raspberry Pi 4 easily integrates with our overall project and works great.
For LCD displays, we decided to go with the Waveshare 7-inch display. We thought that the form factor of 7 inches was enough for our GUI. Originally, we went with the 3.5 inch for compactness, but after using it, we saw it was not a very good choice for implementing a GUI, so we decided to upgrade to a 7 inch, and this was also compatible with our Raspberry Pi 4. This provides us ample real estate to essentially put a nice GUI, and it gives us a nice resolution for clear pictures whenever the user interacts with our display. For micro SD cards, we decided to go with the Samsung micro SD card. We thought the price to performance ratio between the transfer speed and the price, we thought it was a pretty good ratio. We also thought that the size of the micro SD card was well enough to put all the necessary things like our program and the OS itself and our GUI and all the data that we will be obtaining from our receiver. We also thought the read and write speed was plenty enough for our purposes, as the write is about 90 megabytes per second, which is pretty good. And yeah, it was essentially a solid choice for us.
Why we chose software-defined radio is because software-defined radios may be one of the most complex of the 4 types of receivers, but they're complex with good reason. Because of their software functionalities, they are able to detect, filter, and amplify signals that may not even be detected by the other receivers because of how faint the signal the object is emitting, whether it be due to distance from the antenna or size of the object itself. Because of this advantageous property, we must put it in use as different objects emit radio waves at different frequencies. If we have the calculations of a certain celestial body going across the night sky at a certain speed, and we point the antenna at it without a certain frequency range in mind, we could detect many different things and not know whether it is just one object emitting the multitude of radio signals at varying frequencies, or if it is a large number of objects emitting various signals. That is why the more precise, the better. Why we chose the RTL SDR is because it is the most fitting choice for Comet because of its affordable cost and its features that will be sufficient for our goals. Its form factor also makes it a worthwhile choice since the USB connectivity of the RTL SDR allows it to be directly interfaced with the Pi 4 and allows for easy connectivity in a compact form factor. Also, some of the other SDRs that are either no longer available on the market or too expensive to obtain for our uses, and the price doesn't justify its possible selection since most of the features it has will not be utilized as well. So the RTL SDR has the necessary features at an affordable cost. Why parabolic dish antennas? When looking at the complete project scope of Comet, it makes the most sense to utilize the parabolic dish antennas because of their ability to focus the radio signals emitting off of one single celestial object onto the focal point. On the focal point, there is a dipole connected, which will ensure maximum efficiency. Because of this focal point and the concentration of signals onto a singular focal point, the parabolic dish antenna has a very high gain and high aperture efficiency. This is why parabolic dish antennas are the most common form of antennas used in radio telescopes worldwide today. Why we decided to opt for the 3D printed design of a customizable parabolic dish is very simple. We are only restricted by two things, cost and dimensions, when printing this customizable segmented parabolic dish. The cost of the 3D printed antenna will be very low, about $80, but that is because the size cannot exceed a diameter of 50 centimeters. The printed dimensions that we are using are 10 inches by 10 inches. So if we are to make a segmented design with 12 pieces fitting into one another and each piece printed separately, the max length of every piece is 10 inches. Therefore a diameter of 20 inches or 50 centimeters. Based on geometrical calculations, taking into account the diameter of the dish, the focal point of the dish, and the reflective coating of the dish, which is aluminum tape, the estimated frequency range of the 3D printed antenna is anywhere from 100 megahertz to 2 gigahertz. This frequency is very different from the rest of the dish designs because it is not as large. Although the process is complicated, having a customizable 3D printed parabolic dish antenna is very beneficial. Due to the customizability of the design, if something were to go wrong, or if we were to realize this is not the design of the antenna that we want, we can always go back and edit it to fit Comet's needs.
The types of batteries that we decided to use were lithium iron phosphate. This is due to overall safety and also their longer life. And then the batteries that we are using are Furutech Life PO4. This is due to them being supplied by our sponsor. And then we have 3 switching regulators and 1 linear regulator that will be explained later. And then in the power distribution table, this shows the components that we are powering and the regulator that is powering it. For the 12 volt regulator, this takes in the 12.8 volts from our battery, boosts it up to 15, and then puts it back down to 12. And then here we have 1 switching regulator to go from 12 volts down to 5 volts, and then a linear regulator to take that down again to the 3.3 volts for our ESP32.
The stepper driver schematic as shown below was done in Altium. This is the design of a DRV8825 stepper motor driver that will drive the NEMA 17 stepper motors. As you can see, the IC is in the middle, connected with various resistors and capacitors, which are connected to 8 pins on each side, going out onto our main PCB. This is the layout of our stepper motor driver PCB. On the top and bottom, you can see each have 8 pins going out, which go to various spots on the PCB. One of them is input voltage, another is ground. 4 of the pins on top go to the motors. And then on the bottom, we have other pins that connect to the ESP32, which gives it the logic to be able to control the motors and control the amount of steps. If we want a full step rotation or a half step or a quarter step, we can do each of those.
This is the schematic for our ESP32, which also has a USB to UART bridge so that it can communicate to our Raspberry Pi. And here is the PCB for it.
For communication protocol, we decided to go with Serial. We thought Serial was the best and easiest option for us between the Raspberry Pi and ESP32, as we're going to use Serial for flashing onto the ESP32 from the Raspberry Pi. So why not just essentially use the same capabilities of flashing, but instead of flashing code onto the ESP32, we can essentially communicate to the ESP32 with the similar method. So we decided to use that as it was very easy to implement, and we can utilize the USB to UART bridge for more than just one purpose. As for our language choices, we decided to go with C and Python. C and Python were our best choices for the different aspects of our project. For C, we mainly used it with the ESP32 to control our stepper motors. C is very good when it comes to performance, and also it doesn't take up a lot of space on ESP32, which is something that we would have to consider regarding flash memory or like ROM memory. And we also thought it was really fast for interacting with our stepper motor drivers and sending over the signals from the ESP32 to the motors themselves, and essentially able to run our program at the most efficient way as possible. And for Python, even though the performance is a little bit on the lower side compared to C, it doesn't really matter in the aspect of the radio mapping and like the GUI and all that stuff, simply because speed is not necessarily an important factor when it comes to that. But the ease of use is amazing, as Python does provide with a lot of libraries for our different purposes, like communication over serial, radio mapping, GNU radio, things of that nature. So we thought it was very sufficient for our project, and it's also easily readable and easy expandable.
For our mapping software, we have decided to go with the Python mapping software, mainly because GNU Radio, in their code behind, they use Python as the script to kind of generate the flow graph. So we thought this would be the easiest integration as far as using it with our GUI for user interaction, just so that it was smoothly integrated. It's also, the cost is open source. The community support is very active using Python. There's so many resources out there that were very helpful when it came to integrating all of it together and the serial communication with the ESP32 with the GUI. So having that wide support of community engagement was great when we ran into some issues with integrating all of the scripts together. As far as the libraries that were used for Comet, starting with the stepper driver, we used this for ease of programming. So it was really nice to have some control with the motors, being able to use the Arduino IDE to have precise movement for the angles and the speed and the direction. And then for the GNU Radio API, I briefly mentioned before, this was an open source software development toolkit. And basically this provided the signal processing blocks to be able to actually analyze and process the signal that we were obtaining from the SDR. And then lastly, the matplotlib. This was a very powerful plotting library from Python that was giving us the ability to actually plot the signal in the form of a heat map. For our mapping block diagram, so basically the user, whenever they open, it'll be displayed on the LCD display, but the GUI will basically start out where the user can set a frequency. So the frequency can be any value they want to be captured by the SDR, followed by setting the sample rate. So this will be the number of samples taken per second. Once those 2 points are data points are set, then we can start the data collection in the GUI, and this will send basically a message to GNU Radio in the background to start analyzing that signal, processing that signal, and taking in all the data that will be then saved in an output bin file. This output bin file will be read by a Python script that is controlling the actual heat map. Once this heat map is plotted, the intensity value can be seen based off of the dB gain. A strong signal would be plotted by, let's say, the color yellow. Weaker signals would be plotted by a range of colors of like purple or blue.
Our motor control program works as the following. First, we want the user to initialize the system for the three different data points that we need. First being the initial points, the endpoints, and the time duration. Once the user has sent that over, we're essentially able to calculate the necessary data for the tracking phase. So for the tracking phase, we essentially take the start and end points of the X and Y angles and we subtract the difference between the two. And once we subtract the difference between the two, we essentially take the duration of the overall tracking session. We essentially divide that by the degrees, and once we divide that, we essentially have the degrees per second for the motor. So it allows us to essentially know for how many in 1 second how many degrees are we supposed to move. And in the tracking phase, we essentially use that information that we calculated throughout the tracking phase to essentially move the motors in a fashion where it's able to move at a steady pace throughout the whole process. And for the stopping portion, there's usually two conditions for stopping. One of them is that the duration has been met, meaning if the user put 5,000 seconds and once 5,000 seconds is up, we stop the tracking process. Or the user can manually stop the tracking process by sending over a command over from the Raspberry Pi to the ESP32.
This is the 3D printed radio telescope design for our project Comet. We used PETG filament to print the entire radio telescope, and PETG filament is advantageous because it is very strong and also heat resistant compared to other filament types such as PLA because of its high melting point. Aluminum tape is used to cover the surface of the parabolic dish, and it is applied evenly so that the radio waves can reflect off of the aluminum tape and go onto the focal point. The rotating mechanism that is attached on the bottom of the radio telescope is equipped with one 160 tooth gear used to rotate on the y-axis, as well as one 128 tooth gear that is used to rotate the radio telescope on the x-axis, and this is for maximum coverage. The tilt base has a nut and washer placed during the printing process into the print, which locks the rod in coherence with the design thread insert. And as you can see in the bottom left picture, this rod has a counterweight attached to it that is then inserted into that tilt base. The electronics box, as you can see in the top left picture, secures all the electronic components, including PCBs, battery, Pi, fan, and an e-stop or e-switch. And everything is bonded together using super glue because it chemically bonds the plastics together. And then M3 screws are used for the rotating mechanism on the bottom, as well as on top to secure the parabolic dish on top of the electronics box, but also allow for easy removal.
For our administrative content, Carson was in charge of the hardware research and the schematic design, as well as the PCB design and power supply. Alexei was in charge of rotating mechanism design, the 3D antenna design, the motor driver design, and the hardware research as well. Nicola was our project lead. He designed the website. He was in charge of the MCU selection, angling algorithm, and the motor controls. And myself, I was in charge of the radio mapping design, the single board computer selection, the data collection and display, and the communication design. For our current bill of materials, we did change out the potato for the Raspberry Pi, so you'll see a price difference there, as well as we used a different LCD display as before and a different battery. We also had to order our PCBs twice, so you can see it jump in the total there to about $1,250. For our achievements, so on the software side, we were able to establish serial communication between the ESP32 and the Raspberry Pi through our PCB. We were also able to use the GNU Radio toolkit to detect the signal that was reading from the SDR and properly send that to our Python script to be able to plot that data in the form of a heat map. And then for our motor control algorithm, it was able to accurately move the entire dish to where the user had the desired location for tracking. And our GUI was able to compartmentalize all of the software into one place for better user integration. and interaction. So instead of using the Arduino IDE to control the motors and then jumping over to GNU Radio to try to track the signal, the GUI kind of places all of that functionality into one local place so the user can have a better experience with interacting with Comet. But as far as our hardware achievements, our MCU, stepper motor drivers, the 12.8 volt to 15 volt, and then the 15 volt to 12 volt regulators, the 12.8 volt to 5 volt, and the 5 volt to 3.3 volt regulators, PCBs all function very greatly together and they work seamlessly together. Our fully 3D printed parabolic dish is assembled using super glue, and we went outside to test. There was no heat constraint or issues there. So that was a great success on the hardware side, and our focal point was also great to detect the signals. The dB gain for Comet was also excellent, and it met our design specification of 9 dB. And then the built-in electronic box was a bonus, and it was basically made to maintain a compact and sleek design for Comet. That is our project, and we appreciate any questions or comments that you will have for us. Thank you so much for listening.